what we did, right. So watch here. So just to review what we did last day, we talked about specific heat capacity. That's basically the amount of heat energy a particular mass of a substance could take before its temperature changes, right? And we said that specific heat capacity is energy required to change the temperature of a specific mass. Okay, that's what we did last day. Today we're going to find something called a little bit different. You'd recognize that when I heat this substance underwent a temperature change. Okay, so this substance underwent a temperature change, nothing else, right? But if I continue to heat it, what will happen to it? What would happen if we continue to heat, let's say it's a block of ice, right? So if we continue to heat, right? If we continue to heat, then the substance would undergo a phase change, right? When the substance undergoes a phase change, temperature no longer changes, just the phase alone, right? And when we consider phase change, we no longer consider specific heat capacity. We consider something called latent heat, right? L, sometimes use as H. And latent heat, similar definition, energy required to change the phase of a particular mass, right? You'll recognize here, there's nothing to do with temperature change. If we come back here, you will see that the energy required for temperature change is that formula there. E is equal to, right? This is energy for temperature change. Okay, right? So this is what we did last week. We're going to focus on this week, right? So the energy required, if I make E the subject here, right? The energy required for a phase change, right? Energy required for a phase change. Okay, so we're going to focus on this here. There are two types of phase changes that we will learn. One is fusion and one is vaporization. Right? This is LF is solid to liquid, and vaporization is liquid to gas. All right, we are going to focus on these here. I sound like in the lab that we're going to do. Really easy. We'll time it to like a 5 minute top watch, right? We'll see who get the closest to the actual value. Online, they will share some values with each other, right? MLF, MLV, LV, yeah, LH. H is like in general too. So you need to know which quantity to use, right? When a substance undergoing temperature change, you use this one. When a substance undergoing a phase change, you use this one. That's okay? So when you heat the substance, you have to pay attention to which one happening. If it's phase change, just think about this one little formula here. If it's temperature change, just think about this here alone. That's okay? Copy it down and let us try this little lab here when you finish. Okay, someone to explain what we're going to do. Right, so our objective is to find, we want to find latent heat of fusion of ice. Okay, so what we're going to do, we're going to take a couple of ice blocks and we're going to transfer the ice blocks into some water, room temperature water, right? Question, what might happen? The ice will melt, right? So the ice should melt. So for the ice to melt, something has to be supplying heat, right? What's supplying the heat? The water, right? So energy supplied by the water. And who is receiving the energy? The ice cubes, right? Energy received by ice. So anytime you have a question like this, somebody supplying energy, somebody receiving energy. Couple Chris? Oh, no doubt. And we. Right? Oh, yeah. Oh, I watch here. Ready? So what is here? So I want to explain to you what we do. Watch here first, huh? Watch here first. I'll show you the values that we need. Like online, you just have to get them up 10 minutes, right? Because they will get a result and I'll write it down here for you. Right, so energy supplied by the water. Will the water undergo a temperature change or a phase change? The water will undergo a temperature change. So if the water was 30 degrees, would it become hotter or colder? Colder. Right? Would it change phase? Would the water change phase? No. So therefore, if the water undergoing a temperature change, which formula are we using? M E is equal to ML or E is equal to MC that theta. E is equal to MC delta theta. The reason we're doing this is because the water undergoing a what? Temperature change. For the ice. The ice will what? The ice will melt. So the formula we're using is what? ML. In this case, it's F. Because it's going from solid to liquid. Okay with that? So the objective of our whole lab is to find this. Okay, we want to find LF. So LF is what? This divided by this. You see that? Well, of course, bring this here. Okay with that? Yes. Right. So what do we need to get? We need to get each one of these letters. Right. So I just setting up the lab so you know exactly what you have to get. Each person, each group does unit once. We have 3 groups, right? 1, 2, 3 in the back, right? Right. And I will share with the results with those online. So here's what we need. Number 1, we need the mass of water. We need the mass of water. Right? You want to tell me how to get that, right? You need to get specific heat capacity of water. We know that. I gave you that last week. How much it is? Right, but we're using it in grams. So we use 4.2 joules per gram per Kelvin or degrees. Next, we need the temperature change of the water. So we need theta 1. We need the initial temperature of the water. Theta 2. We need the final temperature of the water. Right? And how will you get temperature change, Samir? If we have the initial and the final, how will you get temperature change? Minus them. And? Yeah, you sure? Tired of. Last thing, we need to get the mass of the ice. Okay? We need to get the mass of the ice. Once we have these things, we can find that out. All right? So here's what you have. All I'm giving you, well, all I'm giving them online, I am giving them an empty cup, some water that you will fill in here. So about half, a little more than half, right? About 2/3 because the ice is a big block of ice, right? So I'm giving you the water, right? I'm giving you the, so I'm giving you the water, the empty cup. I'm giving you a thermometer, right? They have, well, you can't see it, but they have a scale to measure, and I'm giving you ice. That's all, right? What you need to do is figure out how to get each one. But what I tell you before you start the labs, so you have an idea, right? So I'm giving you ice, cup, water, thermometer, and a scale. Right? I'll run and get the ice just now, but I want just to start one time when I give you the ice. You might actually do this lab in school. You have different ways to do it. I am using a method called method of mixture. I'll explain that later on as well. Right? In your school, you might use an electrical method. So when you share the results online, we'll do the calculation. And then we'll compare and see who did it the most. But here's what you have to remember. We're checking to see, Christopher, if the ice melts, right? So when you put your water and you put your ice, you stir in. You can leave it a little bit, but keep stirring. Stop, stir until, right? You stir in until you end up with the ice. As soon as the ice melts, you stop. Right? When the ice melts, you stop, you take your final temperature. Initial temperature, that's when you put the water in. The water kind of cooling down right now too. Can't heat up the water, finish faster. Anyway, so you stir in, and as soon as the ice melts, you stop, take your final reading. Okay? But here's the problem. How are you going to measure the mass of the water? How are you going to measure the mass of the water that you put in and the mass of the ice before we start? Huh? So you're going to throw the water on the scale? Measure the empty cup, nice. Put the water inside it. Right. So you need to get the mass of the cup. And you need to get the mass of the cup and the water. Okay? How are you getting the mass of the ice? Okay, this Serena, get all this. Huh? Or again, the mass of the ice. When it melts. Right. Good. Right? So you need one more reading here. Right? You need to get your final, to get the mass of the ice, you need the mass of the cup, the mass of the water, and the mass of the melted ice. Okay, and that will help you get the mass of the ice. Okay, this is cup, water, and ice. I'll show you what to do, right? So there's one group here, one group there, and I'll tool in the back. Do this already, so it shouldn't take long. All right. Do not go more than, don't go too high, right? Go to about 2/3 of the cup. All right. Online, just give them a 10 minutes, and they will post up the results of the lab. I'll record them. I'll put them on TikTok. Get famous. Right. Are you ready? Organizing.
See, when I see that. No, I have call exactly when you see that.
What's that?
Because I call when you see that.
You
You're so excited to show you.
That wasn't joke I was using. I'm too more good. I'm posting. That's like if you want to Mr. Roberts, I'm posting. Right. One group here, two other, right? Get the come on, take every measurements. So get the ice. Right? You have the ice.
So we're not about that.
What? You got lower that,
Please. Watch it next time I get us. Yes, I'm not going to. What the man? Also, I know what's that. Oh my God! Your walk, your walk, your walk. Oh, wait, I can watch. You should know it. What is going on? Good, right? What is good? I know what's happening. Praise will be enough, right? Yes. Oh my days, thank you so much.
Right, let the ice here. Take a little measurements. One block, just one block. Bring plenty, but I think one.
Good. Galaxy one. Galaxy one. Hey.
Oh gosh, let me get a little small thing.
A small thing, a small thing.
I wouldn't show all of it.
Pretty TikTok,
Just put
pretty
the mask
TikTok.
on thing.
Pretty TikTok, bro, pretty TikTok.
Yeah, put your little mask. A little more highlight, right? That's all right. Like, see. You're talking about master again because Tina, so yeah. Are they getting mastered what something already? And the empty cup, right?
Yeah.
Okay.
Oh no. I'm not gonna implement it. Are you right? Yeah, no, sir.
See more than Chico.
Yeah, does he know about that? Does he know? One of my guys.
John 15.8 grams.
115.8.
3.5.
So that makes it be.
Make sure you find the initial temperature of the water low before it drop in the ice. Right, so find the initial way back to go.
I don't know how close I am now.
Right, find the initial temperature before now. I won't take it. All right, high level up. Let's rotate it outside the water. You cannot look at three mercury is still again. That's 20 there, 22, 24, 26, 26 also. Right? But if we did it properly, I guess somebody said 204 or something. I might have 20 and then they go in 2, 4, 6, 8, 1. You're saying that?
26.
That's the initial temperature. Well, I can do it back fast for the one thing. Do it back fast. Right here, looking for the value and you guys pull it down. What's this? Yeah. Yeah.
Yes, you're right.
Yeah, it's not right.
You put the ice ready? Yeah, yes. Please.
Take it out.
You call time never jumping thermometer.
Yeah.
The feet pulling up, double.
Actually, yeah, you could. I get the other service course.
Yeah, good on. It will say temperature. Right, so it's the calculation.
See, you look at so like I had like one where you had to life has limits. Your life has limits.
Yeah, I've done it.
It really selfless. Oh my God. Oh,
Or quarter of the-
Selfless.
Just trying to do that.
I just study when I just like comments on that. I just like read it. Oh, I said what? Simple as that. I think some more motivation.
Okay, I've done it. Right, find its temperature and then put in your eyes, right? And don't forget the kind of mass after. Right, you just do a calculation one time. Come up in the next week, take your values and write it here for me now. Except here, online we'll have to calculate here. You all will have to calculate. Okay, well, let's put your values here, here, here. Put your values, right? I online use these values here, and I want you to calculate the latent heat per month. Positive, correct?
How it going down, right?
Because I
Oh, God.
Let melt and then take it back. You found it mastering water in the cup, right? No, you do that for them. Online will do that. But here and here.
Oh, okay.
Initial temperature,
I eat my side.
right? And final temperature of the water.
See, we don't check this out.
This is right. Final temperature is so low because it's zero.
Yeah, it was over 0 and then it went 2 for
So exactly where it was.
maybe 0 is.
Yes, I eat my
Like 4.5. Not 0. 4.5. I wonder how it's so low that almost zero. These thermometers are a little bit different. 4.5.
That's it.
Yeah. I'm putting mass at final mass. Top water and ice. Right. Online, use these values here and find LF from a place. I'll show you point two.
That's not it, that's not it.
8.6.
Well, it wasn't.
8.2, 8.4.
Oh, God, Sam. Oh, God, Sam.
Look how high, how high is it? It's like totally third or fourth through. 8.6. 8.6 or 8.
3.6, right?
Now, don't make one more. Okay, going to go. Yeah.
Yeah.
Actually. No. Kill that one time. Kill that one.
What is it? Yes.
3 times. Exactly 1 training.
Sorry, I'm working my school.
No, Yeah.
Right on?
Yes, sir.
Melt out. That's your group, yeah. It melt out, right? Take your final temperature now.
Because she was excited. Yes, she was a good excited. Why you told me why didn't we go so? So you could go
So we do in the group, like,
classmates.
Right, final, you got your final temperature, right? Right? Take your final mass. So, if it is less water. 103.8, right? The final mass is 103.8.
Hey, you know.
Right, it's your calculations, and then I want to make one addition to the lab. We do it already, but we're using the same value.
The 1.3. No, I'll make a mistake. Thank you. So it's mass of ice. I do 139 minus 113. I mean 115.2.
Right, do your calculations and quick.
Oh, it's 169.
Right, so I kind of simplify the lab here for you, but there's one more thing that we have to talk about to get the perfect value, right? That's why I didn't write it out for you yet. Right, but if you use your calculations here, what's the mass of the water? What's the mass of the water? Based on their calculation, the mass of the water will be 99.7 minus 2.3. So that value is what? 97.4. Yeah? Use your values, I just using their values. Right? You use your values. Right? They just put in more water than you probably, or less water than you. Okay? The temperature change, delta theta. The temperature change will be 25.8 minus 4.5. Right? I am using their calculations. How much is this? 21.3. Nice. That's your temperature change, and the mass of the ice will be subtract these two. How much is that? It'll be 122.8 minus 99.7. 23.1 grams. Nice. So to find latent heat, all we have to do based on that formula, mass of the water, specific heat capacity of the water, temperature change of the water, all over mass of the ice. Right? So by using what we have there, that'll be 97.4 by 4.2. The temperature change was 21.3 all over mass of the ice, which turned out to be 23.1. Right? Of course, you're using your values, right? How much here? What's here? Online? What's your got? Let me see if anybody work it out online as yet.
Like that.
Use your values alone, right? Remember to use your values, right? So that's 97.4 by 4.2 by 21.3 all over 23.1. Right? Their value is 377.2. And remember, it's energy divided by mass, so it's joules per kilogram. That's not bad at all, but I'm going to show you something I have to change, right? I'll show you the actual value just now. What's all that? All right, work it out. So this value here is group 1. We're going to uncheck group 2 just now. That's Sharpie and there. And group 3. Online, you all follow what I did here to get it calculation. Richie? Yeah, okay. We just waiting on the next 2 groups to hear their values, and then I'm going to make a small correction, well, addition here. Chris, Carol? Go ahead. Work out your group, come over again. Look it out.
Yeah, yeah, it's like 2.5 minus 8. I don't know. Maybe we don't want that.
Right, so group 3, well, yeah, 274.9. Who's all again? 350.42. Right? What's the actual value? Google it. Sorry, gram. Yeah. But why did I write? I write kilograms. Oh, sorry. That's a gram. Right? Latent heat of fusion of ice. Latent heat of fusion of ice.
I get true.
Take it back. Yeah, the actual value is 334, right?
What age?
Huh? The actual value is 334, right? Joules per gram. Right? That's the value you're supposed to get. That's okay? So let's just make one alteration there to fix this, right? But you all recognize all them off, right? Some of them off. We can always fix it. Right, but we have one small thing that we need to adjust. Everybody watch here. Watch here, right? Right. Here we just assumed that the ice melts. But did the ice melt alone? Think about it. When you put the ice in there and the ice melts, what temperature does ice melt at? Ice melts.
What do we see?
Right? What temperature would the ice melt? Anything around 0 degrees, right?
Yeah.
Right? Melts, yeah. Turn to water. Solid. And when it reaches 100, it'll turn to paper. Right? So when the ice melts, and the ice should be at 0 degrees. Right? But what happened at the final temperature? 4.5. So you try to be the ice, right? So this is you here. You are the ice and you melt. Right? Let's pretend you melt. What happens to you against that one? Besides melting. Look at the final temperature. And this water here includes the original water and the melted ice. Sorry? Right, so the original water getting cool and supplying energy, but the melted ice, which is water, what happened to that melted ice? It increased temperature. It was at 0 initially, right? And when ice melts, it will be at 0, right? Technically a little higher than 0, right? And when the water keeps supplying energy to the melted ice, which is also water, it went to 4.5. That's okay? So the melted ice also underwent a temperature change. That makes sense? The melted ice. Because remember, when the ice melts, it becomes water. That melted ice, which is water, didn't stay zero. It increased to this temperature here. Right? So therefore, in an ideal case, our formula should be this. Energy supplied by the original water went towards melting the ice and raising the temperature of the ice. You see that? So this here is the energy supplied by the water. That energy that the water supplied, it did two things. It melted the ice, right? And the ice became water. And then that melted ice also increased temperature. It went from 0 to that final temperature, 4.5. So the hot water or the warmer water went down to 4.5 and it melted, and the ice it melted and it went all the way down to 4.5. That makes sense? So in an ideal case, this is the formula we're supposed to use initially. I didn't want to confuse it yet, right? But now you understand the full thing? Right. So now we're going to use this to solve for LF. Right? So we're going to do over the same thing. It wouldn't change much. It would change slightly. Like this person might get the perfect answer. This person here, group 2, might get the perfect answer. Right? Okay. So let's fix it now. Let's change it slightly and let's see what you get, right? I'm going to adjust it here for you. I'm going to adjust it here, right? That'll do it. Hello? Right here. All right. Nice. So let's see. I'm just going to make LF the subject of the formula, and I'm going to make the adjustments for me, right? So what do I do? In fact, talk to me. Like pick on Vishish. You quiet. Make LF the subject for me. Make LF the subject of the formula. What to do? Yeah, this whole thing is the equation. Move across this whole thing, it becomes what? It becomes minus, nice. So you have mass of water, specific heat capacity of water, temperature change of water, minus mass of ice, specific heat capacity of ice. I'm going to ask you about that. Temperature change of the ice. Yeah, and what to do after? LF. The mass of the ice. Very good. That's good. All right, well, yeah, before I forget, right? For the next 2 weeks, I'm going to try to focus on revising for end of term exams, right? I'll be revising in normal times. I might introduce Tuesday and Thursday, right? And Saturdays, I might do a whole day with my form 5 if I want to join in for a few hours, a whole day and a whole night. Right?
I'll check
Yeah.
it.
Right, so I'll tell you. Right, so they can come one day here and just practice your topics alone. So I'm doing that for next week and the week after, because the exams will be somewhere in between there,
Exam stuff.
right? And I'll be focusing on just the topics. All right, yes, so we have the mass of the water, right? We have the mass of the water, we have specific capacity of the water, we have temperature change of the water. We did that already, right? Do we have mass of the ice? Do we have temperature change of the ice? Temperature change of the ice is this, right? What is the specific capacity of the ice? Think about it. Anybody online can answer as well. What is the specific capacity of the ice? Think about it. It's something real simple. Yes. It's 4.2, the same thing. When the ice melts, the ice is what? Water. So this is really water. Right? Anaya, you okay with this? So all I want you to do is use the values and redo this in my place. Let's see who's the closest. Online, redo the correct thing now, the full thing now.
Like correctly.
Huh? Yeah, yeah, just for correction. I didn't want to give it results yet now. I wanted just to focus on this part here. I want to see if anybody would have realized as well. But you'll understand what's supplying the water and what receiving the water, right?
Yes.
Yeah. Jenny, you follow what happened to the ice when it received the water? Right? When the ice received the water, it melts. And then that melted ice, which is water, change temperature. Okay? So this is the full lab here. Do my favor. Calculate. Let me hear each group. I want to hear what each group got. Huh? How? I'm Felix. I was in a red house was in Austin. I was not red house. When I went to fun, red, I was not purple house. You know, purple house. I was never. No, but she left when I was a kid. I went to the first and then I went to peach. Let's go small dog walk up and think someone else. Oh yeah, do the calculation. I want to hear what each group got. Let's see who was the closest. Y'all figure out where error was. What figure out what the error was. No. Think about this in mass. What was in mass of the ice? Oh yeah. So that was the same. And our initial time. That's what up. Without anybody. Right, group one got 350 now. 350 joules per gram. Group two, what you all got?
334.5.
Hey, for the ratch.
For
For the ratch.
Oh.
That's the actual value all again.
I cheat sheet. Yeah, hold on. I'm sure I have it.
334 point
0.55.
0.55.
0.52.
Alright, 0.5. And group 3. How much all again? So group 2. Group 2. Except Vichy, but he didn't have to do anything. Vichy didn't have to do nothing. Alright, online for the value that you would have worked out would have been in 350, right? What shall I get? 248. So yeah, it will be smaller than the first one. 248.9. You're just everything was the same except for the smaller mass. So if it had less water, then this temperature change should have been a little smaller. Because the mass of the ice is the same. I gave you all almost the same mass ice. So it's only here I suspect something probably happened, unless you all read the temperature values of wrong. Right? That's the only thing. I think that this is the only thing that should have been a little bit different for you. Temperature change. All right, nice. So this is how we handle questions like this. And the method that we use here is something called method of mixtures, where we took a solid and mixed with a liquid. Okay, so you can make a note of that, right? The technique that we use here was something called method of mixture. All right. So again, in method of mixtures, in fact, it's anything that you're doing. Something supplies energy, something receives energy. Okay? Anybody remember what conservation is this? Conservation of energy. Okay? Energy is neither created nor destroyed, right? So something has to supply energy, and then of course something will receive the energy. In our example, the ice received the energy, the ice underwent a temperature change. So we have phase change first and a temperature change. Okay? So that's something important for us to remember, right? All right, nice. So again, to summarize this whole thing, whenever something undergoes a temperature change, we use E is equal to MC delta theta. Whenever something undergoes a phase change, we use ML, MLF or MLV. Everybody okay with that? Yeah? Right, technically what we did here was a past paper, right? I'm going to select it fine, time you do it. Right, and I was watching you all doing the lab, right? There's some simple things that you all doing wrong, right? Reading temperatures wrong, taking thermometer out of the liquid to read the temperature, right? You have to pay attention to those little things, right? So for example, right? If you took the thermometer out of the water and took its temperature, you are actually finding the temperature of the surrounding as opposed to the water, right? And you keep stirring just to make sure the ice melts. All those small things will show your values off. Right, but somehow the two still manage to get the same value. All right. Watch this here. See if this sounds, see if this looks familiar. See if this looks familiar. This is, oh, I don't know why here. Right, you see? Or you can do it. Take a little read. So they want you to find the latent heat and zoom in a little bit more, right? Because you will need, oh wait, somebody show me how to zoom in. First one. Huh?
Try on the phone.
Try what?
No, don't try that, don't try that, don't try that. Don't try that.
Pause what?
Pause that phone.
Alright, do that for me now. Take those values and find the latent heat. You have everything you need there in those two lines. Two little lines there and you have everything you need. Online, message your answers. Just try to break. So what was the latent heat capacity of ice? Jalen, the actual answer was 334. Right? Presman got 334. Lakshman get 248. And Arithia students get 3. All right, Jalen. So the actual value was 334. I don't know why yet. Let's work it out now. Let's put 26.
All right. You should really come back.
Beautiful calculation. Let's see what you get. You're using the same 4.2 for specific capacity, right?
No, wait, you mustn't do that.
So that's good. When the formula change, same formula, because what's supplying the heat? What's supplying the heat? The water. What's receiving the heat? The ice, and the ice did two things, right? The ice underwent a phase change and a temperature change. All right? Right? So we need all the values again. Right? We need all the values again. We need number one, we need the mass of the water. Actually, let me categorize it here so you can see online. I'm sure again. Six. That sounds like it. Huh? 34? What are you gonna sum? Right, so latent heat of fusion using the same formula that we had before, right? What's the mass of the water here? 100. What's the specific capacity of the water? 4.2. What's the temperature change of the water? The water went from 30 degrees to 20 degrees, so that's 10. Minus mass of the ice, which is 10 as well.
Yeah.
Mass of, sorry, specific heat capacity of the water, which is 4.2. And what's the temperature change the ice underwent? Chris? 20, yeah. 0 to 20. The final temperature of the ice, the melted ice, is 20 degrees.
Oh.
Okay? Right? So it's from 0 to 20. So the final temperature or the change that the ice underwent is 20. And then divided by the mass of the ice with 10. Right? And there you'll get your answer. What they got online? 336 which you've got. Jadon, what you got? Right? Teresa got 336. Right? When I work it out, I got 336. What's the SI unit again? Joules per gram. March. Wait, March. 31st last week, March. When you okay with us? Online, you all okay with this? Anaya, Arisa, Celine, Jenny, you all got these values, Serena? We have one more to squeeze. Everybody okay, right? Chris, are you okay? Stefan? Right, we have one more, but I was missing one of the pictures here. I thought I could do this one. I think I can do this one. All right, there's one little thing here about this here, huh? And it is all right, take a little read here. 1 point. 1 point. The whole squad then
160 or 161.
who in it
You read host. Curious red.
All right, take a little read. Tell me how we doing this here. This is the last one. Take a little read. Don't answer yet. Let's pick somebody online. Let us pick somebody online, right? Right? Before you figure out, before you write the formula you're going to use, check and see, Vishish, if it's a phase change or a temperature change undergoing, right? Right, to pick online here. Let us pick Lakshmi. What's the formula we're going to use to find heat entry here, Lakshmi? What's the formula we're using to find heat? Look at it, there's only two formulas that we have. You have to figure out if this substance underwent a temperature change or a phase change. Lakshmi, you there? Mr. Ryan? Lakshmi, you there? Lakshmi, not there. Jilan, help me out now. All right, now let's pick Mitchell. Nathan? Mitchell? What's the formula we're going to use here? Right, good job, Keelan. Right, Keelan said phase change. Right, Keelan said phase change to the formula we use it is equal to ML. Right, what letter we use it? F or V? V. Go ahead. Right, how we know is not temperature change? Vishish. How we know is not temperature change? You can measure it. Vishish, how we know is not temperature change?
Right here.
Right, how we know is not a temperature change? Huh? How come we know it's not a temperature change? No. We did good. Everything right there. Why is it not a temperature change? Huh? And what else? Can we say quietly? Well, then one comes up is so, you know. We did good in this line right here. One sentence you have to read. Huh? No, something easier. How you know it's not temperature change? In the meantime, while we work it out. Right. Temperature remain the same, 100 and 100, right? That one turns going.
It's fluid.
One turns going on the mind. Vishish work out it thing now, boy. Man, it's cool the way it's cool at two different times and different. You don't know. Oh yeah. What's the mass? This is going so slow, Vishish. What's the mass? Right? And what is the latent of vaporization? Somewhere around there. Anyway, let's use them. This space it out bad.
Like 2.3 million.
Oh, that's fine. 3 million. Based on the-
1, 2, 3. But how do you write the letter?
I don't know how to write that.
But how do you write the
Right? Use their value, 3 million, right?
big value? Yeah, really. Yeah, got it.
What's all again?
1, 2, 8, 4.
Look, give me standard form now. Give me standard form. Right? Try to give me the value in standard form. Right, just 1.84 by what? 10 to the 8?
Yeah.
Okay, 8. Right, what's the SI unit? Joules, right? Energy. So it's just joules. All right. So we'll continue to do a few of these next week. Right? And finish up this part of it, right?